Hello everybody and welcome to today's lesson on the empirical rule and z-score percentiles. Today's objectives are we will identify properties of a normal distribution and apply those properties to determine probabilities that are associated with areas under the standard normal curve. So what does the empirical rule say? The empirical rule states that if we have data that is normally distributed, and in the real world all data sets that consist of a sufficiently large number of data points happen to actually be normally distributed, in a normal distribution we have fixed percentages that are associated with areas under that normal distribution. Here we do see our normal distribution curve. In the middle we got mu, our average or mean, and then we can mark the areas to the right and to the left with successive numbers of standard deviations that we are away from the mean. So to the right we are +1, +2, +3 standard deviations, and to the left we are -1, -2, and -3 standard deviations. So the empirical rule states that 68% of data is within one standard deviation of the mean. That means from one standard deviation below to one standard deviation above. And don't do that shading yourselves, as we're going to be redoing this a couple of times. So this area under our standard normal curve is associated with 68% of the values. 95% of the data is within two standard deviations of the mean. From two standard deviations below the mean all the way up to two standard deviations above the mean. This area underneath our curve represents 95% of the data, and 99.7%, so almost 100, but not quite 100% of the data is within 3 standard deviations of the mean. That represents this entire area underneath our standard normal curve. Knowing this, and also knowing that the normal distribution curve is symmetric, we can break this down even further and assign probabilities to each one of these areas underneath the curve. So between -1 standard deviations and the mean, we have 34% of the data. On the other side of that, we have another 34%, which add up to 68. Then going to the left, between -2 and -1 standard deviations, we got 13.5%. And towards the right, the corresponding area also has 13.5% of all the values. Between -3 and -2 standard deviations, we therefore have 2.35% left. And the same to the right. And our very outskirts represent 0.15% of the data to the left, and another 0.15% of data to the right. These percentages are always the same for every normal distribution, no matter what the data in the distribution actually are, and we can use that to find probabilities for values that are above or below a certain border or within certain borders. And that's what we're going to start practicing now. Suppose a set of test scores for 50,000 students. That number is definitely large enough to be normally distributed. And it tells us here that too. With a mean of 81 and a standard deviation of 2.5. What region of the graph would represent 23,750 below average students? Below average means that we're looking to the left of our mean only, and we are trying to find an area that represents 23,750 of those 50,000 students. So let's first find out What is that as a percentage? 23,750 divided by 50,000 comes up to be 0.475. In percent, that is 47.5%. We know that the area right to the left of the mean represents 34%. That's not quite enough. And if we go one further, we have 13.5%. Adding up 34 plus 13.5, we get 47.5. So that is exactly the amount we needed. This area here represents 23,750 students whose test scores were below the average. Let's look at an example from biology. The lifespans of turtles in a particular zoo are normally distributed. The average turtle lives 91 years and the standard deviation is 21.4 years. Shade the regions under the curve for the turtles living longer than 48.2 years, and approximately what percentage of turtles lives for longer than 48.2 years. First of all, we need to mark our normal distribution curve appropriately so we know which area we're really talking about. The average, we're told, is 91 years, and the standard deviation is 21.4 years. So if we move to the right, we have one standard deviation above the mean would be 91 plus 21.4, and that's 112.4. Two standard deviations above would be 133.8, and three standard deviations above would be 155.2. To the left, we have one standard deviation below the mean, that's 64.6. Two standard deviations below the mean, 48.2. Three standard deviations below the mean, 26.8. And the number that we were looking for is 48.2. This is what we care about, and we want to shade the region under the curve for turtles living longer than 48.2 years. So to the right of that, to the right of 48.2 years is all this part of our normal distribution curve. And now we're supposed to find out what percentage is represented by the shaded area. Now in those types of problems you have two different ways of doing it. You can either look at each of the shaded regions, look up their percentages and add them all up together, or you can take 100%, which is what the entire curve represents, and subtract the areas that we don't need. That really depends on the problem, and as usual, mathematicians try to do the least amount of work, not the most. So in this case, I suggest we take 100 and just subtract the two areas that we don't need. 100 minus 2.35% and minus another 0.15%, and that gives us 97.5%. 97.5% is the percentage represented by this area, and that is the probability that a turtle lives for longer than 48.2 years. Alright you guys, so much for the first part, and now go ahead and watch the second part of this tutorial.